Okay, welcome back. So this is the second video in this series of how to lead ID a Delta 9 lead motor. So hopefully this is making sense to you. Okay, so we're on step 4 and on a new page, and what we're going to do is label the terminals of groups 2 and 3. So let's just write down what I just said. Label the terminals of group 2 and 3. And there's going to be 4 little bullet points that I'm going to write down here, and then I'll explain them later. So we're going to apply 15 volts. That's a 15. 15 volts to T4 and T9. And I'll explain that in a bit. And then we're going to measure induced voltages in all 4 windings of groups 2 and 3. And I'm just going to bring this down here. Label T5 and T8 with the highest voltage. Relative to the group. And then we can label T7 and what is it, T6 by default. Okay, let's bring back our drawing here. So I'm just going to redraw this. Great thing about videos is you can speed them up if you find this going too slow for you. Okay, so last video I had my benchmark, the T1, T2, and T3 labeled. So let's bring that back. So we got D, I, and C. So that's where we left off. Now let's see what we're doing here. We're going to label the terminals of groups 2 and 3. So this is group 2, and this is group 3. And might as well put this in, and this is group 1. So yeah, we tend to go in a clockwise fashion when we're talking motors a lot of times, you know, T1, 2, 3, and so on. Okay, so we just labeled those groups. Now we're going to apply 15 volts to T4 and T9. So we have to know where T4 and T9 are. So just looking for a pencil here, and I must have dropped it. Okay, now from our previous page, we know that D is the center point, and I'm just going to bring back the previous page here. D is the center point between A and G, so that can't change. We can't just make up some new letters. We know that the wire A is connected to D, you know, through this winding, and also G. The problem is we don't know if this is A or G or this is A or G. But we also have to look at, so apply 15 volts to T4 and T9. Sorry, I skipped a step here. So first of all, we have to know what the terminal labeling is. So this is T4 and this is T9. And that is done in a previous video or steps that you guys have learned. You can also search the internet. This is a standard. So this is T1, T4, T7, T2, T5, T8, T3, T6, and T9. So I would memorize those things. So I'm using that terminology to help us with this process. So we're applying 15 volts to T4 and T9. We know how to do that would be to apply it to G and A. And again, we don't know which one is G or which one's A, but we do know that we can apply 15 volts there. So let's write that in first. So 15 volts. Now, where are you getting 15 volts from? Good question. In the classroom, we have something called a variac, which is just an adjustable voltage, and we can bring 120 down to 0, 5, 10, 15 volts, all the way up to 120. Now, out in the field, what you could do is use a doorbell transformer. It's not 15 volts. It'd be more like 24 or 30, depending on how beefy it is, but that would work. I've seen people use 120 volts too. It's just you got to move this thing around a bit, and 120 volts is a little dangerous, but it can be done if you're careful. In the classroom, we're going to stick with 15 volts, and that's how our labs are set up. Okay, let's move forward. So we're looking at this step here. We're taking some kind of source, voltage source, and we're connecting it to the G and A terminal. Let's just write that in too. That is going to be, G and A terminals. And that's just for this motor. That's not for all motors. It just happens to be this motor G and A are connected to D, and we're going to label them as T4 and T9. All right, now after we put a source voltage T4 and T9, we are going to measure the induced voltages in the other groups. And yes, that will happen. So you got to remember, you guys have some transformer theory here. What's going on is all these windings are crammed under the housing of a motor. And so even though a motor is different than a transformer, there's still some overlapping physics going on here, that when we apply a voltage let's try that again. When we apply a voltage to these two windings, that magnetic field is going to cut across these other windings, and it's going to induce a voltage into these 4 other windings. And with the way it's set up, we can actually figure out which winding is which due to the relationship physically in the stator here, because these are all stator windings. All right, let's go down our list here. So measure the induced windings of induced voltages of all 4 windings. And then through that, we can label. So let's just do a little side chart here of our groups 2 and groups 3. So group 2, it was labeled B, I, and H, and group 3 was labeled E, C, and F. And where am I getting that information? Again, from back here. I was the center point of group 2, and C was the center point of group 3 with those letters corresponding. And I'm just copying that information over here. So now, again, I got a source voltage to T4 and T9 here, or G and A, I should say. And I'm going to take some measurements. So once that source voltage is hooked up, I'm going to take my voltmeter in AC, and I'm going to measure between I and B, and I'm going to take a reading. And what was my reading? So I got 1.5 volts between B and I. And then I'm going to move my meter leads. I'm going to read the voltage between I and H, and I got 5.6 volts. Then I'm going to go down between E and C and measure, and I got 5.8 volts between those two. And move it over to C and F, and I got 1.4 volts. So those are all my measurements and all my readings. Now let's go back to the step here, and it says label T5. So we have to know where T5 is. And in pencil, I'll just write that in. T5 is here. Actually, let's just write in all of them here so you guys know what's going on. So what it says is measure the induced voltage. Okay, we did that. Label T5 and T8 with the highest voltage of each group. So here's T5 and here's T8. So let's look. Now remember, I and C can't change. That's our benchmark. So they are always going to stay. So let's go with the the group 2 winding here? Well, between I and H is 5.6 and between I and B is 1.5. So it says with the highest voltage, label in this case T5. So does it make sense? I is attached to H, that's the highest voltage. So this is going to be 5.6 here. We don't really care about that as much as labeling T5 with the letter H, because this is going to be the highest voltage. Now, by default, and I'm skipping to this step here, I can label T7 because I know that the B letter is attached to I on the other side of H. So this has to be the B letter because H and I have the highest voltage across it. Now the 1.5 volts between I and B, I mean, it's important in the sake that it's less than 5.6, but that's it. We're just looking for the highest voltage across this winding here. And then we're going to do the same process over here. So hopefully you guys can tell me what's going on. So C to F is 1.4, C to E is 5.8. If we want the highest voltage from T3 to T8, then it makes sense that this would be the E terminal, and then by default this is going to be the F terminal. Okay, just a little background, and this might not actually work in reality, but it's still a great way to think about it for you out there that are saying it doesn't happen like this. So if I put my pen across here where I'm applying the voltage, so I'm applying the voltage right there, and I'm thinking of a winding that's straight across. Now we know in transformer theory that if we have a winding, and I'll just use my hand as boring as it is, as let's say my primary, and then I have a secondary. Now if you ever rip apart a transformer, well, usually the windings are over top each other, but sometimes those core made ones, they'll have a winding on one side and a winding on the other side, and they're always going to be parallel with each other because you get a better cut of magnetic flux from the conductors. If I have the winding, let's say perpendicular, I'm not going to have as many wires cut, and therefore I'm going to have less voltage induced. So the moral of this story is, if you have two windings in parallel, you're going to have a higher voltage than if the windings are perpendicular to each other. So let's use that kind of theory with what we're doing here. These windings, I guess there's 4 of them in total, but let's just say 2 windings. They're parallel with each other, so that's why these windings are going to be induced a higher voltage, because these other ones, they're not quite perpendicular, but they're not parallel, so they're going to have a less voltage induced into them. So that will give you some kind of way of thinking about this when you do this process, that this going straight across here and this going straight across here will be parallel, higher voltage in these phase B windings here. Okay, I'm going to